The next third case, third derivation. So we are finished with both the ends hinged and both the ends fixed. So next is case 3. One end of column is fixed. One end of the column is fixed, and other end is free. So initially, let us consider the straighter column, the straight column AB, in the AB of length L, column AB, which is having the length L, and it is fixed at one end. It is fixed at one end. So we'll just fix the end end A, fix the end A, and it is free at the other end. Okay. So we are going to apply the load at the free end. So that is a Euler load or buckling load, which is P. Let P be the Euler or buckling load, which is acting at the end B. Okay. So after applying this load, the column is deflected with respect to the support. The deflection of the column, it happens like this. The column is deflected. So this yellow part shows the deflection of the column. Okay. So as the load will be acting, so this load, the same load will be acting at the end of the column. So this load will be placed here. Okay, after applying the load will be at the end of the column. Okay. So after deflection, so when the load is applied, the column is deflected. Let us consider some section to find the buckling load which is acting in the column. So let us take a section at any part. So let this be the section X, okay, which is at a distance. So this section is at a distance small x, small x. And due to this applied load, initially this is the column, the white line what I have written. So this is the actual column. After application of the load, the column has deflected or it is deflected. Along this section, let the length of this deflection be y. So this deflection along this section x be y, small y. Okay. And there is also a deflection at the free end. Let the deflection at the free end be A. It is deflected by some distance. So that distance we are taking that as a constant. At the section X, it is Y. At the section, it is, at the free end, it is A, small a. Okay. So let us find the moment, a bending moment at section X at X. So at this section, the moment is 1. So moment is mx x, that is equal to the force at this point, the moment at this deflected point. I want to find the moment at this particular point. Okay, with respect to this point. So the distance will be this distance. The distance will be this. Okay. So the force is P. The moment at this particular point is, I want to find, that is at this particular point, it is mxx. Okay. So what is this moment? Force into distance. Force is P. So this distance will be A minus Y. A minus Y. Since I want to follow the sign convention, the sign convention in this case, it is positive. Since I have a convex part of the bending with respect to initial portion, this convex part, with respect to sign convention for the column, since I can find the convex portion of the beam which is deflected with respect to initial support. So this is taken as positive sign convention. Sign convention is positive. So it is positive. So whereas in other two cases, it was deflected in this manner, the beam was deflected. So you can see the concave part with respect to initial column, so it was negative there. So here it is a convex part with respect to the initial column, you can see, so it is positive, the moment is positive. So the moment value, it is force into this distance, so it is plus P into distance is A minus Y. So I can get the moment at this particular point. Okay. Next. So I know this, the moment, the bend, the deflection of the beam with respect to deflection of the beam, the moment at any section, the moment at any section, it is given by EI d square y by dx square, which is equal to PA minus PY. I just cross multiply these terms. So EI d square y by dx square. Just take P into y to this side. It is equal to P into A. Next, the general expression or general solution for the differential equation, for the differential equation. So we know that the general solution for this differential equation, it is C1 cos x into root of P by En plus C2 sin x into root of P by Ei plus we have P into A term. So when P by Ei comes to this side, so it will be remaining with only A. Or you can reduce this to one more term equation. You can reduce this equation to one more form, or d square y by dx square minus p by ei into y will be equal to p into a divided by ei. So this p by a will get cancelled, will be remaining with only a. Okay, this is the equation for deflection y. So
Sir,
call
plus
this as
PY.
equation. ಯಾವುದು
Sir, RHS and LHS ಬಂದ.
ಇದು ಇದಾ
ಸರ್ ಮೇಲೆ
y equation ಏನು ಹೇಳ್ತಿದ್ದೆ?
ಸರಿ ಸರ್ PA minus PY. RHS and LHS ಬಂದ.
PM
ಪ್ಲಸ್ PY.
ಇಲ್ಲ,
ಅಲ್ಲ ಸರ್.
ಇದು ಸಾರಿ okay, correct. So this is ei into this ಈಚೆ ಬಂದಾಗ it is plus p into y into a, right? Okay, the general expression for this you need to remember. So ಎಲ್ಲ ನಾಲ್ಕು derivation it is same, only with respect to constant you need to know that whether it is only a constant or ಇಲ್ಲಿ ಏನು term ಬರುತ್ತೆ, with respect to that it will be Okay, next, differentiating this above equation dy by dx, differentiating dy by dx is equal to differential of cos, it is minus sine, so minus c1 sine x root p by ei, so it is, and also the differential of this x into root p by ei is root of p by ei plus differential of sine is cos c2 cos x into root of p by ei into the differential of x into root of p by ei is p by ei, root of p by ei, constant it is 0. So call this as equation 2. So this has 1, this has 2. So now you should apply the boundary conditions with respect to both the equation and find out the integral constant C1, C2. So boundary condition at the fixed end, that is x is equal to 0 at here, x is equal to 0, there is no deflection. There is no deflection at this particular point. So y will be equal to 0. And also, there is no slope at the fixed end. Since there is no deflection, the slope of the curve is also 0. So that is the first boundary condition. This can be, I'll rub this. Okay, apply the boundary condition. Apply boundary conditions at x is equal to 0 at the point A. So we have deflection, y is also 0, and also dy by dx. Slope of the curve is also 0. Okay. So apply that boundary condition, apply x is equal to 0, y is equal to 0 for equation 1. So by equation 1, so if I apply here, so y will be 0, c1 cos 0 is 1 plus sine 0 is 0 plus a. So it will be 0 is equal to c1 plus 0 plus a, right? So if I find c1 will be equal to minus a, c1 will be equal to minus a, right? Next, from equation 1, next by equation 2, you apply the boundary condition for the equation 2. So that is dy by dx is equal to 0, dy by dx is equal to 0 by equation 2, that is 0, dy by dx is 0. So if it is x is equal to 0, sine 0 is 0 plus c2 plus c2 cos 0. This is x, cos 0 is 1. Therefore, it is remaining with c2 into this term, c2 into root of c by ei. Okay. So now I want to find the buckling load or Euler load. So this load cannot be 0 here. So that is C2 into root P by EI will be equal to 0. So when I compare this, so P cannot be equal to 0. Since I want to find P is not 0. Therefore, C2 will be equal to, since P cannot be equal to 0, therefore C2 will be equal to 0. Since I want to find the equation for P cannot be equal to 0. So since C2 will be 0. So next you apply this C1, C2 in equation 1. Therefore, y will be equal to C1 is minus A. C1 is minus A cos x root of P by EI plus C2 term is 0 plus A. Okay. So by applying the boundary condition at the point A, I got the equation which is reduced and I have found the constant C1, C2. Next, you apply the boundary condition at the free end. At this free end, x, this distance will be equal to L. X will be equal to L. And what about y? Deflection. This deflection of the curve, y will be equal to, at the free end, it is A, right? So apply this. I'll be using with respect to equation what I got. So at x is equal to L, at x is equal to L, deflection will be equal to A. So apply this boundary condition to the equation what we got. So y will be equal to A, x is equal to L. So A will be equal to minus A cos L root of P by EI plus E, right? So when I apply the boundary condition to this equation, the above equation, so this is the what I got. So you can take cos to other term. Therefore, A and A gets cancelled. Therefore, A cos L into root of P by A, or you can also take A outside. You can also take A outside and you can solve. Or A gets cancelled, right? Okay. So when I type cancel A into cos L root plus A is equal to minus A plus A. Right? So now this gets cancelled, it is 0. So this term will be 0 or A cos L root P by EI will be equal to 0. So when cos theta will be equal to 0? When is this cos theta will be equal to 0? Or you can also write A, when A goes to other end, it is 0 by A, it is also equal to 0. Cos L root P by EI will be equal to 0. So I want this term will be theta. So when this term will become equal to 0, when I substitute cos theta will be equal to 0, that is cos theta will be equal to 0 when theta will be equal to 90 degrees, right? Whether it is 90 or it is pi by 2 or 3 pi by 2 or 5 pi by 2 like this. So this term L into root of P by EI when it becomes equal to pi by 2 that is 90 degree or when it is equal to 3 pi by 2 or when it is equal to 5 pi by 2 any odd term 5 pi by 2 etc. So this term theta will get or that is L into root of P by EI will be equal to 0. will be equal to 0. Therefore, I'll be taking all these are positive terms, so I'll be taking the first term. So therefore, L into root of P by EI will be equal to pi by 2. When I do squaring L square into P by EI is equal to pi square by 4. So just rearrange the terms, you will get the equation for P. If I rearrange the terms, you will get the equation for P. So I'll write here itself. So when I rearrange, so P will be equal to pi square EI. So this will goes to the other end. It is pi square into EI divided by 4L square. 4L square, or you can also write 2L whole square. 2L whole square. So this is the final expression for Euler load or buckling load when one end of a column is fixed and other end is free. So you need to remember that to solve the problem. So next, last one, case 4. That is one end of a column is fixed and other end is pinned or hinged. Another end is hinged. The same thing, let us consider initially a straighter column, a column which is straight, it is, let AB be the column which is having length L. Let the length of the column be L. And let the end A be fixed. Let the end A be fixed. And another end B is hinged. Another end is hinged. It is hinged. So let the load P is applied at the end B. At the end B. So due to this applied load, the column is deflected Okay, as shown. The column is deflected as shown here. Okay. Okay, due to this, there is a resisting moment at the end A. This we are learning. There will be a moment at the end A. There will be a resisting moment M naught at the end A. Okay. To overcome this resisting moment at the at the hinge support, there will be a reaction, horizontal reaction force that will be acting. To overcome this resisting movement, to balance this movement, effect of movement, there will be a resisting force, that is horizontal force, that is set at the hinged end. Okay. So now let us consider any section. So let us consider a section X, which is at a distance. So which is at a distance small x from the fixed end. Okay. So when this is x, so another the top portion will be L minus x. So this total length is L. So this remaining length is L minus x. So now let us find the moment at the. So now we want to find the bending moment at the section X. Bending moment at XX. Okay. Since it is deflecting such that there is a concave surface with respect to the initial beam, you can see the concave surface here at the inside nearer part of the beam. So with respect to initial beam, the concave surface is with respect to the initial beam facing. So therefore the moment will be negative here. So with respect to the previous third case, it was positive since there was a convex surface with respect to initial beam, it was positive. Here it is concave surface with respect to initial beam, it is negative. Therefore that is MXX. MXX is the bending moment at the section X, at the section X, and this deflection not shown here. So let this deflection be Y. Y. Okay. So the moment at this surface, at the section X, it is load is P, P into the deflection is Y. The deflection is Y. So there are two forces. One is there is a reaction horizontal force as well as there is a applied that is Euler load. So you need to consider the effect of both. So the moment with respect to this, it is load into the distance Y. It is P into Y negative. Y negative, it is concave surface, it is with respect to initial beam, so it is negative. Next, there is a horizontal moment. That is, horizontal force is H into, with respect to section X, the distance is L minus X. L minus X. This plus H into L minus X. That is the moment that is acting with respect to the reaction, horizontal reaction. So it is H. The distance with respect to this section X, it is L minus X. We know that the moment at any section X, it is EI d square y by dx square is equal to minus py plus h2 into L minus x. So just cross multiply all the terms. We will be remaining with d square y by dx square plus P by EI into Y plus R, that will be equal to H by EI into L minus X. H by EI L minus X is a constant. So the general solution, we know this general solution for this above expression, general solution so just as similar to last three cases, we have C1 cos x into root of P by EL plus C2 sin x into root of P by EL. So the remaining is constant plus H by P. So EA gets cancelled. P will be going to denominator H by P into L minus X. That is Y, equation for deflection. So call this as equation 1. So next differentiating that is dy by dx will be equal to minus C1 sin x root P by EI. Differential of x root P by EI is P by EL plus C2 cos x root P by EI into root of P by EI. And there is x term here, L minus x. So if you multiply this P by H into L, it is a constant. So P by H into minus x, the differential it is minus H by P. Okay, call that as equation 2. So then it is, you need to apply the boundary conditions to get the constants. So apply the boundary condition at the fixed that x is equal to 0 at the point x is equal to 0, deflection y is 0, and also the slope of the curve at this point is 0. dy by dx is 0. You apply that, you will get C1 and C2. So boundary conditions at x is equal to 0, y is equal to 0, and dy by dx slope is also 0 at the point A. So by equation 1, so if you apply here for equation 1, so 0 will be equal to C1, this term will be 1 plus C, this term will be 0 plus 0. So it will be remaining with HP by N. So that is 0 is equal to C1 cos 0 is 1 plus sin 0 is 0 plus HP into L minus 0. So HP into L. So C1 will be equal to minus HL by P. Okay. Next, you apply the next second boundary condition for equation 2. That is, with respect to equation 2, apply the boundary condition. That is, dy by dx is equal to 0, x is equal to 0. So by equation 2, dy by dx is 0 is equal to minus C1 sin x, it is 0, sin 0 is 0, plus C2 cos 0 is 1, cos 0 is 1 into this term, C2 into P by root EI minus H by T minus H by P. So you just cross multiply, you will get a solution for C2. So C2 will be equal to, so when this goes to other end, so C2 will be equal to H by P into root of it is reverse, EI by P, right? So now you substitute the terms in the equation 1, substitute the terms in equation 1. So that equation 1 becomes what? Y will be equal to, so C1 is minus HL by P minus HL by P into cos x root of P by EL plus C2 is HP by H by P into root of EI by P into sin x into sin of x root P by EL plus HP by H by P into L minus X, right? So now you apply the second boundary condition at for this equation where we got this constant and we substituted here. So now you apply the next boundary condition, that is at x is equal to L at this point. X is equal to L at this point, at the point B. The deflection is 0. Y is also 0 at this point. So apply this second boundary condition at x is equal to L, y is equal to 0 to this above equation. Okay. So you apply this, this will be reduced. So when y is equal to 0, so that is 0 will be equal to, so x is equal to L minus h by p into L cos L root of p by EI plus h by p root of EI by p sin L into root p by EI. Right? When you substitute x is equal to L, this term will be 0. This term will become 0. So we are remained with this here. So now you just rearrange the terms. Rearrange the terms. So if I rearrange this, if I take this is minus. If I take the other end, it will be plus. This will be plus. So that is h by p into L cos of L root p by EI will be equal to h by p root of EI by p sin L into root of p by EI. E by EI. So here just cancel the common terms. H by P is common there in that equation, right? So I just cancel. So then you'll be remained with what? You'll be remained with these are the constants, that is L and root EI by P. And these are similar terms, cos theta and like sin theta. just take to other side. So I'll be writing here. So I'll take this to the left hand side. I'll cast to the right hand side. So it will be like P by EI, root of P by EI into L will be equal to sine L into root of P by EI divided by cos L into root of P by EI. It is like sine theta by cos theta, right? So what is that? Sine by cos is tan, right? Sine by cos is tan. I can write, so this is L into root of P by EI is equal to tan L into root of P by EI. So it is like theta, L into root of P by EI is theta. So that is, it is like theta is equal to tan theta. It is like theta is equal to tan theta, right? So when theta will be equal to tan theta, so we have some value that you need to remember. That is, when theta will be equal to, when theta will be equal to, theta will be equal to 4.4935 radians, then theta value will be equal to 4.4935 radians. Just for your, you need to remember this. When theta will be equal to 4.4935 radians, so this theta will be equal to tan theta. You can substitute in your calculator. Nearly it will be equal to. Nearly it will be equal to tan theta. So the tan theta value and this value will be same when you substitute this in radians. Radians. So when the value of theta is 4.4935 radians, the theta will be equal to tan theta. Okay. Therefore, I'll write here. Therefore, let L into root of P by EI is equal to theta, or L into root of P by EI will be equal to, so nearly let us consider, so this value, so nearly equal to 4.5. I cannot take this all full fraction, let us take nearly equal to 4.5 radians. So therefore this L into root of P by EI, let it be equal to 4.5. 4.5. So when this becomes equal to 4.5, this theta will be equal to tan theta. So let us consider this term as theta, so that theta will be equal to tan theta. So we have taken the theta value as 4.5 radians. So therefore, you do squaring. So L square will be equal to L square into P by EI will be equal to 4.5 square, 4.5 square. So 4.5 square is nearly 20.5. Therefore, L square into P by EI is equal to that value. So 20.5 is nothing but it is 2 pi square. The value for 20.5, if you do it 2 pi square, it is safe. So therefore, let us take that. Therefore, it will be equal to L square by EI. Cross multiply, you will get an equation for P. P will be equal to 2 pi square divided by L square EI. May be wrong. EI 2 pi square into EI divided by L square. Right. So just with respect to other expression, if I want to make it similar with respect to other expressions, So we had P is equal to pi square EI divided by L square by 2. Okay. This is the expression for Euler load or buckling load for one end of a column is fixed and other end is hinged. So out of these four, in all of the papers, you will get one derivation almost.